Ultralight Aircraft. The ultralight aircraft occupies the entry point of powered aviation, the smallest, lightest, simplest category of machine with an engine attached to a wing. Regulatory definitions vary by country, but the common thread is strict weight and speed limits that define a class of aircraft anyone can learn to fly with minimal training and operate without the full licensing requirements that govern heavier aircraft. The engineering brief is radical simplicity. A small engine producing between 50 and 100 horsepower driving a propeller attached to a basic airframe that may be as minimal as a hang glider frame, with a motor or as developed as a small enclosed cabin with rudimentary instruments. Ultralights have brought powered flight within financial reach of people who could never afford a conventional aircraft. The purchase price is closer to a motorcycle than a car, and the operating cost reflects a machine that burns fuel at a rate measured in liters per hour rather than dozens. What ultralights sacrifice is range, load capacity, and weather tolerance. They are fair-weather aircraft limited to short flights and calm conditions. Within those limits, they represent something the aviation industry has rarely managed to deliver: a flyable aircraft that a person of ordinary means can actually own and operate. The ultralight made flight affordable. The propeller aircraft made it practical, and it has been doing that job longer than any other powered machine in the sky. Propeller aircraft. The propeller aircraft is the machine that made aviation practical, and it remains the dominant form of powered flight in terms of sheer numbers of aircraft in operation worldwide. A rotating blade converts engine torque into thrust by accelerating air rearward, pulling or pushing the aircraft forward through the atmosphere, where wings generate the lift that keeps it airborne. The simplicity of that mechanism, combined with the mechanical reliability that piston and turboprop engines have achieved over a century of refinement, has produced a category of aircraft that ranges from two-seat trainers to the Lockheed C-130 Hercules, a four-engine turboprop that has been in continuous military service since 1956 and shows no sign of retirement. Regional turboprop airliners, the ATR-72, the Bombardier Q-400, connect smaller cities and remote communities across the world on routes where jet economics do not justify the operating cost, carrying passengers on shorter hops that the jet network was never designed to serve. Propeller aircraft dominate short-haul regional aviation, agricultural operations, aerial survey work, firefighting, Coast Guard patrol, and the general aviation sector, where private owners require an aircraft that is economical to run rather than optimized for speed. The propeller aircraft is not glamorous by the standards of what follows it on this list. It is simply the workhorse of flight, doing the majority of the world's actual flying, while the jets get the majority of the attention. The propeller aircraft built the foundation. What came next didn't just improve on it. It changed everything about what flight could be. Jet aircraft. The jet engine changed everything. Where a propeller converts engine torque into thrust mechanically, a jet engine generates thrust directly, compressing incoming air, mixing it with fuel, igniting the mixture, and expelling the exhaust at high velocity through a nozzle in a continuous cycle that produces forces no propeller-driven aircraft could match in speed. The result was a doubling of practical aircraft speeds within a decade of the jet's introduction in the 1940s, and the opening of the entire supersonic flight regime that propeller aircraft could not physically enter. The Boeing 707 cut transatlantic crossing times in half when it entered service in 1958, and the commercial jet airliner it represented has been the backbone of global air travel ever since. The Boeing 737, the Airbus A320, the Boeing 777, the Airbus A380, carrying hundreds of passengers between cities on every continent every hour of every day. Every commercial flight most people have ever taken has been on a jet. Every long-haul route connecting continents depends on jet engines producing the thrust required to sustain a fully loaded aircraft across thousands of kilometers of ocean. At the extreme end of the same category, the Concorde sustained Mach 2 in commercial passenger service for 27 years, and the SR-71 Blackbird cruised at Mach 332, where its standard response to a surface-to-air missile launch was simply to accelerate. Both are jet aircraft, both using the same fundamental propulsion principle as the Boeing 737 carrying 180 passengers between regional airports. The breadth of what a jet engine makes possible, from the most ordinary flight a person is likely to take to the fastest sustained, manned flight in history, is the measure of how completely the technology transformed aviation. Every aircraft so far has needed one thing: a runway. The next one was built specifically for the places where no runway exists. Seaplane. The seaplane solves a problem that every other aircraft on this list simply accepts as a given: the need for a prepared runway. A seaplane takes off from and lands on water using either floats attached to a conventional airframe or, in the case of the flying boat, a hull shaped to function both as fuselage and as a boat hull, capable of generating the hydrodynamic lift needed to accelerate to flying speed across a water surface. The category opened up aviation to vast regions of the world where runways did not exist and building them was impractical. Coastlines, island chains, remote lakes, and river systems that are inaccessible to conventional aircraft. The Catalina flying boat of the Second World War patrolled ocean areas so vast that no land-based aircraft could reach them, conducting search and rescue, anti-submarine operations, and long-range reconnaissance across the Pacific. Modern seaplanes continue to serve remote communities in Canada, Alaska, and the Pacific Islands, where they remain the primary connection to the outside world. The limitation is the water itself. A seaplane needs relatively calm conditions to operate safely, making it weather-dependent in a way that runway aircraft are not, and the drag of the hull or floats imposes aerodynamic penalties that reduce speed compared to equivalent land aircraft. Helicopter. The helicopter is the aircraft that goes where fixed-wing aircraft cannot. Vertical takeoff and landing from any surface large enough to accommodate the rotor diameter, hover in place above a single point, fly sideways, fly backward, descend into spaces that no runway-dependent aircraft can reach. The helicopter's operational flexibility comes entirely from its rotor system, which makes it independent of runways in a way that every fixed-wing aircraft on this list does not. The engineering price of that independence is complexity. Each rotor blade must change its angle of attack multiple times per revolution to generate lift evenly around the full circle of rotation, a problem solved by the swash plate, which adjusts blade pitch continuously as the rotor spins. Helicopters serve emergency medical evacuation, offshore oil platform crew transfer, search and rescue, military assault and reconnaissance, firefighting, and urban air transport in conditions where fixed-wing aircraft simply cannot operate. The machine that does all of this is slower, less fuel efficient, and mechanically more complex than any comparable fixed-wing aircraft. In the environments where it operates, none of that matters. The helicopter redefined what vertical flight could do. The next aircraft took that same problem, stalling at low speed, and solved it in a way nobody expected: Autogyro the Aussie. Autogyro occupies a category most people have never encountered, and that the aviation industry has never fully decided what to do with. It has a rotor like a helicopter, but the rotor is not powered. It spins freely in the airflow generated by the aircraft's forward movement, a phenomenon called auto-rotation, generating lift without any engine connection. Forward thrust comes from a conventional propeller driven by a piston engine. The result is an aircraft that cannot hover and cannot take off vertically, but can fly at much lower speeds than a fixed-wing aircraft without stalling and land in extremely short distances. The autogyro was invented by Spanish engineer Juan de la Cierva in 1923 as a solution to the stall problem that had killed numerous pilots. A freely rotating rotor cannot stall the way a fixed wing can, making the autogyro almost impossible to crash through loss of lift at low speed. It never achieved the commercial success its inventor imagined, largely because the helicopter arrived shortly after and offered genuine vertical flight capability that the autogyro could not match. It occupies a niche today among enthusiast pilots who value its unique combination of low-speed stability and mechanical simplicity. The autogyro could not hover. The Tiltrotor was built to solve exactly that, and combining everything the helicopter does with everything a fixed wing. Aircraft does better. Tiltrotor. The Tiltrotor is the aviation industry's most ambitious attempt to combine the helicopter's vertical flight capability with the fixed-wing aircraft's cruise efficiency in a single airframe. Its rotors are mounted on nacelles at the wingtips that rotate, tilting forward for fixed-wing cruise flight and rotating upward for helicopter mode hover and vertical takeoff. The V-22 Osprey, operated by the United States military, is the only tiltrotor in widespread operational service, and its development history reflects how genuinely difficult the concept is to engineer. The program ran for over 2 decades and suffered multiple fatal crashes during D.